Everyone. In this lecture, we will discuss about special or miscellaneous kinds of reactors which are used in industries. One of them is recycle on a reactor. Recycle for a plug flow reactor or any packed bed reactor or any tubular kind of reactor. This this is very common in use. Now, before we deal with recycle of reactor, what is recycle? Recycle is using of the effluent stream of a reactor again mixed with fresh feed and then put into the reactor back. Now for recycle there is a recycle ratio which is defined as the volume recycled to the volume leaving the system. Now suppose a typical recycle, this is a plug flow reactor. This is inlet stream having molar flow rate of A Fa naught. This is point 1 and this is point 2. And suppose the molar flow rate at point 1 is Fa naught prime. Suppose the volumetric flow rate inlet of the system is Q naught and volumetric flow rate leaving the system is Q. We are assuming there is change in density, means epsilon A term is not zero. This is a general case. Now, if the outlet effluent volumetric flow rate is Q, then as per recycle definition, this must be RQ, as if this has to be RQ, because R, then we will get volume recycled, which is RQ, divided by volume leaving the system, which is Q, again getting back R. So to get back R, this must be RQ and this is Q. So if the system leaving has a volumetric flow rate Q, then the recycle will be RQ. This is easy to remember. And suppose for this PFR, we consider PFR as a system. Now, if we consider PFR as a system, PFR as a system of interest, then inlet is Fa naught prime and outlet, this inlet point is point 1 and this outlet point is point 2. Okay. Now, Fa in for any point inside the reactor along the volume of the reactor. Now suppose any flow rate inside the PFR, let it denote be Fa prime. Fa prime, which denotes the inside flow rate at any point, Fa prime. Fa prime, this will be equals to Fa naught prime 1 minus Xa. Xa is the conversion at this location, at certain Xa location, which is a function of volume. So this will be our expression for molar flow rate of A inside the PFR. Now at point 2, suppose the conversion is XAF. Now this is the conversion which will be the leaving the system. So this is same conversion which is leaving the system. So if the system, overall system, inlet is Fa naught, inlet is Fa naught and outlet is with outlet of the system is XAF, having conversion XAF, then we get an expression like this: FAF, this is the final outlet molar flow rate of A is equals to Fa naught 1 minus XAF. This is one relation we will get, and point 2, Fa 2 prime prime denote that this is inside the recycle system. Fa2 prime, that is the outlet of the PFR, will be equals to Fa naught prime 1 minus XAF, which will be again equals to. Now, see one thing, if the reactor outlet is having volumetric flow rate Q, then this will have concentration CAF and this will have concentration also CAF. Remember, this is a splitting of stream, so composition will be same. So composition will be same. Composition will be same. So QCAF is nothing but FAF. So volumetric flow rate into concentration of A final. F denotes subscript F denote final. This will be final, which is the leaving, which is the concentration leaving the system. So if this is FAF, now one thing to note that the the molar flow rate at point 2 will be RQCAF plus QCAF. This is molar flow rate of A at point 2, which will equals to this term that is going to recycle and this term which is leaving the system. Now, if we write QCAF as FAF, then it can be written as R plus 1 FAF, which is, if now again putting this FAF expression here, we get R plus 1 Fa naught 1 minus XAF. Now, if you look this expression, we can easily relate. We can easily relate from this above expression Fa naught prime. This we are relating this one and this one. Fa naught prime is equals to R plus 1 Fa naught. Now this is very important relation. This equation 3 tells that the inlet molar flow rate of A will be R plus 1 inlet molar flow rate of fresh feed. Fa naught is the fresh uh, fresh molar flow rate of A. Now we will do. Now we will also relate. Now we want to actually calculate what will be the conversion of XA1. What is the conversion at XA1 related to the whole system? This means we are trying to find the, as this is a recycled feed, the converted product is recycled back to the system. So at point 1 there will be some conversion relative to the overall system. So to find the conversion of XA1 relative to the overall system, we will write again the expression. Suppose the at inlet at XA1 we will use the equation from equation 1, from 1 if A1 is equals to if A naught prime 1 minus XA1, which is equals to. Now if you look at 1, there is term there is one term fresh feed which is going and this term which is adding. So at 1 the fresh feed which is Fa naught fresh feed plus RQ QCAF. Now QCAF is FAF. We will write is FA naught plus R FAF, which is equals to FA naught plus from FAF, from equation 2, from 1 and 2. FAF is R into FAF is FA naught 1 minus XAF. Now, using relating these two expressions, dividing by FA naught prime 1 minus XA1, my target is to find XA1. So FA naught plus R FA naught 1 minus XAF divided by FA naught prime, FA naught prime 1, 2 and again 3 using third equation 3. This expression FA naught prime is R plus 1 FA naught. Now FA naught gets cancelled, 1 plus R 1 minus XAF divided by R plus 1. Now if you solve for XA1, which will get 1 minus 1 plus R 1 minus XAF divided by R plus 1, which is equals to, we simplify it, R plus 1 minus 1 minus R plus R XAF divided by R plus 1, which is equals to R by R plus 1 XAF. So XA1 is R by R plus 1. So with relative to the whole system, conversion at point 1 is R by R plus 1 XAF. Now we will use this expression if a prime, if a, sorry, if a prime which is equals to if a naught prime 1 minus XA from 1, from 1, if a prime is equals to if a naught prime 1 minus XA, if a naught prime we get that R plus 1 if a naught 1 minus XA. Now we know that for PFR the equation is differential equation is F a prime by dV is equals to RA. Now if we simplify this expression, R plus 1 F a naught dxa by dV is equals to minus RA. Now if you write dV by F a naught is equals to dV by is equals to R plus 1 dxa by minus RA. Now to get the volume of the recycle reactor, we will writing V by F a naught is equals to R plus 1 will come out of the integral. It we will integrate it from XA1 to XA final because at inlet of the PFR there is a conversion XA1 dxa by minus RA. Now if we put the value of XA1 we get the expression R plus 1 integral R by R plus 1 XAF to XAF dXA by minus RA. So we get the volume expression for a recycle reactor V by Fa naught is equals to R plus 1 R by R plus 1 XAF to XAF dXA by minus RA. This is the volume expression for a recycle reactor. Now recycle reactor, not recycle reactor, recycle across a plug flow reactor. Now if you see the expression, two limiting case, R, R, R tends to 0, gives pure PFR, and R tends to infinity. If you do R tends to infinity and use L hospital rule, then this will give CSTR. If you do limit R tends to infinity, there will be infinity by infinity form, and use L hospital rule here. You will get V by Fa naught is equals to XA at final divided by minus RA evaluated at XA final, which is equals to, if you do R hospital rule, then you will get expression V by Fa naught is equals to XA final divided by minus RA evaluated at XA for R tends to infinity. R tends to infinity. This is a expression for CSTR. So this recycle, how we control gives PFR or CSTR or somewhere in between. So this is one type of reactor, and this expression is in general case. There is no assumption made that epsilon is 0. So this is general case where epsilon A not equals to 0 also valid. So density changes are taken in care because we have dealt with only molar flow rates. Now we will talk about another types of reactor called packed bed reactor. Packed bed reactor. Now packed bed reactors are used mostly for gas phase reaction in industry. In packed bed reactor, this is also fall under a continuous flow reactor, and it is fall under category of tubular reactor where packing of catalyst are present inside the reactor, and gas flows inside the system. Gas flows inside the system with certain molar flow rate, and there will be, and there suppose this distance is x, and these catalysts have weight, total weight W total is equals to 1 minus pi, which is sorry 1 minus wait 1 minus epsilon 1 minus epsilon volume total into rho catalyst, density of catalyst. This epsilon, this is porosity, this is catalyst density, and this is the total volume of reactor. So this is total volume of reactor, and at a suppose this distance is x, and at x plus dx, this is x plus dx location. The weight of the catalyst present will be dw is equals to 1 minus epsilon rho catalyst bv. Right. Now this is in this case also material balance will be same. This is x plus dx location. Molar flow rate of A entering, molar flow rate of A exiting is this. Now this now in this case the rate of reaction will be in terms of per gram catalyst. This is mole per meter cube per second per gram catalyst. So rate of reaction will be based on this unit. The unit of Ra, let me denote it by prime, will be mole per meter cube per second per gram catalyst. Because the reaction happens when the reactant is in contact with the surface. So this can be also expressed in the meter square of surface, but it can also be written expression of per gram catalyst. These conversions can be found in many textbooks. This is just a rate of reaction in different terms. I can even also write rate of reaction per volume of catalyst, per volume of the reactor. This is all same. It only depends how you want to evaluate express the rate expression. Now let me suppose the rate expression is in terms of per gram catalyst. So by doing material balance Fa plus Ra prime dW, that is generation is equals to Fa plus dFa. There is no local accumulation, so we get dFa by dW is equals to Ra prime, which is again equals to minus Fa naught dXA dW equals to Ra prime. This is for single reaction. For single reaction, now suppose now Ra will be function of conversion and temperature. Now the concentration gas phase is defined at point X. At X point X, concentration of A is Fa by total volumetric flow rate. Now which is equals to Fa naught 1 minus Xa divided by the volumetric flow rate. Now as we have discussed earlier during uh, mole balance, to get the volumetric flow rate, we will assume that the gas behaves ideally. PQ is equal to FRT and P naught Q naught is equal to F naught R T naught. Now, if we divide these two equations, we get PQ by P naught Q naught is equal to FT divided by F naught T naught. Now we know that F is equal to F naught 1 plus epsilon A XA for single reaction. This expression is for single reaction. So we get 1 plus epsilon A XA T by T naught. Now Q is equals to Q naught P naught T by T T naught 1 plus epsilon A XA. Now we will put this value of Q here. We get Q naught P naught T by PT naught 1 plus epsilon A XA, which is equals to Fn naught by Q naught P PT naught divided by P naught T 1 minus XA divided by 1 plus epsilon A XA, which is equals to CA naught, that is the inlet concentration, PT naught divided by P naught T 1 minus XA divided by 1 plus epsilon A XA. Now if you see the expression, I have written that minus Fa naught dxa by dw is equals to Ra prime. Now reaction rate depends on concentration Ca, function of concentration Ca, Ra. Now this function has both pressure term, temperature term, conversion term. So Ra will be actually dependent on both Xa, temperature and pressure. So we got a differential equation relating conversion Xa, but we have no equation in terms of temperature and pressure. Now for pressure, we can do momentum balance across the packed bed reactor, or by doing some analysis, momentum balance, or we can also use Argon equation. Argon equation is also a result of momentum balance. Argon equation is the final result of momentum balance across the packed bed reactor, but with certain assumptions. This is not a proper, but with certain assumption, with some experiment, it is found like that. Now the Argon equation, we know that pressure drop per unit length minus sign is because dP differential of P is negative. To get this term positive, because the RHS of the Argon equation is positive term, minus, let me write it properly, minus dP dx is equals to 150 mu V divided by pi s squared particle diameter square 1 minus epsilon divided by epsilon cube, and this is square, plus 1.75 rho V square divided by pi s, this is sphericity into particle diameter, into 1 minus epsilon divided by epsilon cube. Now this is the Argon equation. This equation has both laminar and turbulent flow condition. The first term is laminar term, laminar. This term is turbulent, inner. This is superficial velocity. V is superficial velocity, means volumetric flow rate by area cross section. Now we will simplify this expression. This 150 sphericity, particle diameter, the porosity epsilon, the sphericity, all are constant. So we can write this expression in terms of single constant, and also this velocity is superficial velocity. We can replace v and v square as q square by area cross section square. So area cross section of the packed bed reactor is also constant. So we can directly write this expression as sum alpha 1 volumetric flow rate plus some beta 1. Note that this is density, gas density is variable, so we cannot consider it at a constant. This gas density will vary along the x of the packed bed reactor beta into, so we'll write beta into beta 1. So beta 1 into rho q square. Okay. Now, now we all know that the mass balance law will satisfy. Now mass balance means mass flow rate will be rho into q is equals to rho naught into q naught. So rho naught into q naught. Now rho naught, rho naught is equals to rho naught is equals to q naught by q. Mass flow rate will be constant, so we will simplify or modify this expression as like this beta 1 uh, rho q whole square divided by rho. Now rho q whole square is mass flow rate square. This is another constant, so I will write it as alpha 1 q plus beta prime into 1 by rho, because rho q is mass flow rate which is constant. Now rho is rho naught into q naught by q. So we can again simplify this expression alpha 1 q plus beta prime rho naught, sorry, beta prime divided by rho naught, beta prime 1 by rho naught q by q naught. This is the expression. Now, yes, now we can modify this as again like alpha 1 q naught q by q naught plus beta by beta prime by rho naught q by q naught, which will again become another constant alpha 1 q naught plus beta prime by rho naught into q by q naught, which is again, suppose this is a beta, overall beta q by q naught. Now beta can be evaluated from this expression or any correlation from experiments in industry. Generally the pressure drop for a reaction is you can do experiment and get. Now beta q by q naught, again q by q naught is given by this expression, q by q naught, wait, q by q naught is given by this expression, this q by q naught is given by this expression, which is p naught t by pt naught into 1 plus epsilon x a beta into p naught t by pt naught 1 plus epsilon a x a. So we get a final expression minus dp dx is equals to beta p naught t by pt naught 1 plus epsilon a x a, and beta is equals to some constant which is alpha 1 q naught plus beta prime by rho naught. Now beta prime and all those have those extra terms. We can easily backtrace those terms, so I am not writing those terms. Now I want to replace this dx with the differential of weight. If you replace the dx with differential of weight, uh, dw is now dw is 1 minus epsilon rho c into dv. Now dw is 1 minus epsilon rho c into area cross section dx. dv is area cross section dx. So I can easily write minus dp by dw is equals to dx. dp by dx 1 minus epsilon rho c a c beta T naught T by Pt naught 1 plus epsilon A xa. Here epsilon is for single reaction, change in by mo- change in the stoichiometric coefficient by molar by stoichiometric coefficient of A into Ya naught. This is to be known. This is delta. Now, if we this again can be written as some P naught T by Pt naught, some beta naught 1 plus epsilon A xa. So here we get another differential equation. So we get two equations minus Fa naught dxa dw is equals to Ra, which is xa pressure, temperature. Another equation we got minus dp dw is equals to some beta naught T naught T by Pt naught 1 plus epsilon A xa. Now, is the temperature, this entire packed bed reactor is in isothermal condition, that means temperature is constant. If T is equals to constant, then solving these two different simultaneous coupled differential equation will give the all required variables like variation of pressure, variation of conversion you will get. But if temperature is also not constant, a reaction is highly exothermic or something like that, temperature profile will change across the bed. Then you have to use another equation, which will be energy balance equation across the packed bed reactor to get the ex- uh, uh, differential equation relating temperature and enthalpy of reaction, which we will not do here because non-isothermal conditions we will discuss later the effect of temperature. But if the temperature is constant, in most cases, temperature is kept constant in the packed bed reactor, then we will be able to get that pressure and conversion profile from these two coupled differential equations. Now some extra things like mean residence time. Mean residence time is defined as for a tubular reactor, the volume divided by volumetric flow rate at certain location. Let me write it correctly. These are certain extra term like mean residence time. This this is important while discussing about the residence time distribution. For mean residence time, which is the average time spent by the volume of fluid inside the reactor. Suppose this is the plug flow reactor, and in this volume dV, it has volumetric flow rate Q. Now, the mean residence time is the volume of the volume is the time spent by the volume of the fluid parcel at dV volume. inside the reactor. The mean residence time dt bar can be easily found by dv by q, that is the time spent at the dv volume by the fluid, which will be again equals to, if we write the main expression dfa by dv is equals to ra. From that dv we get as dv is equals to dfa by ra minus ra into q. Now dfa is fa naught dxa divided by, I am writing the minus term in the bottom, ra into q. And for constant temperature pressure, if the temperature pressures are constant, or if it is not constant, let me write the non-constant term, fa naught dxa divided by minus ra. Now q is that is q naught p naught t by pt naught. So we will write q is equals to p naught t by pt naught q naught 1 plus epsilon xa, which is equals to, now fa naught by q naught is concentration naught, pa naught dxa divided by p naught t by pt naught 1 plus epsilon xa. Hence the total residence time of the fluid T bar is equals to ca naught 0 to xa final, which is the exit, dxa divided by p naught t by pt naught 1 plus epsilon xa. This is the final residence time expression, the mean residence time. PT pressure temperature profile can be solved for any PFR or packed bed reactor using material energy and momentum balance. So this expression will give the mean time.